including ports, transportation, water supply, sewerage, transmission lines, hydropower, industrial projects, and dam rehabilitation. He is a valued member of both the Indian Geotechnical Society in New Delhi and the Institution of Engineers in Kolkata. We are truly privileged to have him share his insight and rich professional experience with us today. Please join me in welcoming Mr. Shrikar Vaishampyan.
Let's start. Yes, you require. I don't. Okay. Hello. Good afternoon to all. I would like to thank Epicons for giving me this opportunity again to present my views actually on the subject matter. I hope that you will find them reasonably satisfactory. I would also like to thank uh, our director, Jayant Kulkarni, Anand Kulkarni, Arvind Purulekar, Parashar Moge, P.P. Pandey, and least of all, Mr. R.D. Deshpande. They are all been long-time association, and my knowledge grows with most of the projects I participate with Epicons. So I would request Jacinta to share the PPT. Yes, today's subject is fundamentals and practical aspects of lateral earth pressure. I found that after the conclusion of the last webinar, it seems that participants and from the Epicons, Friends of Concrete, had singled me out for answering these questions. Of course, I welcome that because that is naturally because of the nearness and the friendship in the company. What I have done here is that I focused basically on the basic concepts, then how we carry out designs of the different retaining schemes or retaining methods, and I think that is long enough or big enough at the moment. So let us proceed slide by slide. Yeah. Next, please. Yes. So the retaining walls, as we know, sorry, let's get back to this thing. There are basically two types of structures. The structures which are, it is normally what happens is the structures are supported on the soil. The foundations, the column loads actually goes onto foundation and the structures are supported on soil or rock stratum. But then next, you'll find that in the retaining systems, the retaining walls are the ones that provide support to the soil. Basically, what tends to happen is many times the excavation, we have to keep it near vertical or vertical. When you are trying to keep the excavation vertical, it is definitely going to collapse. Under those circumstances, we actually have to raise the retaining structure, and basically that means here the structure supports the soil. The foundations in foundation case, the soil supports the foundation. This is the other way around. In this case, the structures support the soil or rock. So retaining systems are the ones which are basically laterally loaded structures. Now, in these two retaining systems, there are two basic systems. One are non-embedded and the second is embedded. Now, let me elaborate further on in the next slide. Yes, the non-embedded type is the basic type of retaining wall we are all familiar with. This is basically what happens is when you're going to construct a non-embedded type retaining wall, you are going to excavate up to a foundation depth of the retaining wall. Then you are going to construct the retaining wall. And after construction of retaining wall, you are going to fill the soil back. So that's why it's called backfill material. So it will derive stability from what? It will derive stability from basic self-weight of the structure. Then sometimes the weight of the soil on the heel. Then the passive pressure for the part which is below excavation depth. And sometimes if the passive pressure is not sufficient, you will tend to provide a shear key beneath the foundation. And lastly, the SBC of the founding stratum. These are the factors which will tend to provide stability to the retaining walls. Next slide, please. We'll see some examples now, typical. A gravity retaining wall. The first one is the basic gravity retaining wall. Gravity retaining wall is the one which was done probably in age-old times using masonry. The structure itself was self-sufficient. By itself, the gravity wall means the dead weight of the wall itself will be sufficient to keep the structure in stable condition. In the semi-gravity wall, you will find that the section is reduced and you provide a reinforced section on the front. You can see the steel reinforcement there in the front, and yes, you can see this steel reinforcement at the front, and it actually the same. It's a very similar to gravity wall. After that, you will find that cantilever type of walls are used. Cantilever walls are like when you started using concrete and you moved on from masonry, stone masonry to concrete, you will find that people got knew that they can now handle the bending moments and shear forces. So they started with the base and a thinner stem to save cost. And the soil that was kept on top of this would impart stability. Now the third is that as and when you put or you let us say you go on increasing the height of the retaining wall. When you go on increasing the height of retaining wall, the bending moment will be too much or too high to retain within this section. Therefore, what would happen is you needed to provide a tension member behind. Now, these tension members are called counterforts. But if ample space is available outside, that is on the other side of on the excursion side, then you put a member in compression that is called buttress. So these additional members, which will, when they are in tension, they are called counterforts. When they are in compression, they are called buttresses. Buttresses were used in stone masonry wall. Let's go to the next slide, please. You'll see some examples now. Yeah, a standard stone masonry walls, what you can see by roadsides in many of our places. You can see this is a ground sloping upwards here, and this is a practically compound wall, but this is actually a retaining wall on the other side because the soil is filled up here. You can see some of these in Hiranandani's complex also, and this is a brick wall, not able to carry that much of tension, so we are trying to divide it in different panels. So the buttresses which are going to remain in compression are provided here at uniform distance. Next slide, please. On the other hand, the gravity wall, so when you moved on to concrete, actually from the masonry or bricks, actually, you started using the concrete. And a typical example of gravity concrete wall would be a dam. And you all must be knowing about Koina Dam. Koina Dam is basically a gravity structure. It was considered as a stable, and it got damaged during the earthquake in 1970. And then it was strengthened, and then buttresses were added. So these are the buttresses which are in compression. They are outside. When the earth pressure comes from other side, this remains in compression. Next slide, please. Okay, so the typical RCC cantilever retaining wall. Now, this is you're quite familiar with. Most of you people would be familiar with this kind of material, this type of retaining wall. I can see this is possibly 10 to 12 meter tall, at least 6 meter tall retaining wall. The person is standing here, assuming that person is about 1.8 meter tall. You can say this is around 6 to 7 meter tall retaining wall. Such a cantilever wall is possible. Now, there are variations because of site constraints. You can see that this is the one in which they have put counterforts inside, and you can see tire marks here. So this is the area that's going to be filled up here. So you will fill up this area, and these counterforts will provide you the necessary stability. On the other hand, you can have a L-shaped wall that is without toe. There is no toe, only heel, and you are going to fill the soil here, and the weight of you can see the weight of the wall is very nominal. That means the soil which is filled up here is going to impart maximum amount of stability. There is another side of the picture there. When you come to the other side of the picture, you will see sometimes that when you have an excavated rock face, you will not have probably have space to have the heel part of the retaining wall. So quite a few times you end up with having a outward L, or there is only with the toe and the stem. Only these two elements are present in this. This type of retaining walls are also possible. Now, how are the stability imparted to that? We'll see in the further slides. Okay, then these are the flexible reinforced earth walls, flexible walls. In the non-embedded type retaining walls, they are flexible. You can see here that they have used MSW, that is a mechanically stabilized walls or reinforced earth walls. In this, you put a geofabric or a geonet or a geoweb and place a layer of soil on that, compact it, place another layer of geoweb, geomembrane and compact it. That way, you can go on building this. You can see that a nearly 8-10 meter height of the wall or maybe more than that is standing here practically vertically. And this is quite common now. And I'm sure that while going by the side of the flyover, you would have seen these type of constructions very frequently in Mumbai, outside Mumbai, everywhere in India now. With development of NTPC, you will see a large number of such constructions being executed right up to height of 15-16 meters also for approach embankments. Next slide, please. Yes. This is another form of flexible reinforced earth wall. The gabions, which are known to us, like when you pass from Mumbai to Pune, you will see in the Ghat section, you will see many such boxes of the stone kept there. They are known as gabions. Companies, the vendor companies like McAfee, and which is one of the very famous companies. But other companies also offer this kind of service, and you can design this. A typical design of McAfee, this kind of gabions, you can look at this. What it does actually is that we have a height h, and the base width would be not less than 0.6 times the height, and then you provide a small offset of say 0.1 meter to 0.45 meter while going up, and that and a certain minimum top width. Now the certain minimum top width will not be less than width of one gabion, that is about at least 1 meter or maybe more than that. Or this can be arranged in different forms, and you can get very stable system here, because for this backfill, since this has gone below ground level, it is not possible to slide. It actually offers all the, shall we say, perfectly stable solution, and yet it is flexible. This allows water to flow through. This allows local repairs, and this is one of the very versatile constructions. Next slide, please. Okay. Now we have seen certain number of the embedded non-embedded type walls. What is the meaning of non-embedded type wall? By this time, you must have realized that these walls don't penetrate into ground and derive, shall we say, substantial amount of resistance from soil. On the other hand, we have a different type of wall here, which is an embedded retaining wall. The embedded retaining wall, what it does to us is that you have to install the wall first before the excavation is commenced. You drill and install the thing well below excavation depth, and only after ensuring that you have sufficient factor of safety or safety of retaining element, you can actually carry out the excavation. This is a method we use very frequently now for different basements in urban areas. Like you must have also seen many such drawing issued by your office or by our office also sometimes. Now these elements are stabilized by passive pressure developed on the embedded part of the wall. That means, let us say that you are going to have excavation, depth of excavation is h, then you start installing the pile or a retaining element which will go through h plus certain embedment depth d, and that embedment depth d can be how much? That can be as much as 0.75 to 2 times the height of retaining wall. Now this is true in case of purely cantilever embedded retaining walls. Now what are the typical examples in the past? The typical examples were sheet piles. Everybody says, are we going to do sheet piles in this our site? Are we going to do sheet piles in our site? So the first instinct is, because you have read about something about sheet piles in textbooks, you will come up with the query, are we going to do sheet piles? But then there are also diaphragm walls or meter panels, which is a concrete variation, and more practical and more employable or more useful retaining piles are also used as a embedded retaining walls. Next slide, please. Yes, now I'll show you some examples of these retaining walls, how they are actually installed. You can see in this picture, the walls actually are installed side by side, and a sheet pile, a section of certain shape like this. This much is a section shape, and it is installed by locking into the adjoining member. You can also see here, that there is a interlock, like there is a kind of interlock like this. When the next slide is put inside this, this goes right inside and push through right and right. So there is a, you can see this is the interlock position. Now this, when loaded or after excavation, tends to tighten up and provides nearly watertight excavation space. Now I'm using nearly watertight. Remember this. Now you must be wondering what this is. Okay. So basically what happens is this retaining part, when you're trying to drive sheet piles, you can do sheet piles very well up to SPT value of from starting from 10 right up to 30 in the sands primarily, or also in clays. But if the SPT value is higher than that, then there is a need to loosen the soil to some extent. And this function is done by pre-boring operation in the at the location of the next sheet piles. When you do a pre-boring, the soil tends to loosen up because you have actually disturbed the soil there, taken out some soil, reduced the density. Now you can drive the sheet pile comfortably. So that is the purpose of doing the pre-boring like this. Next slide, please. There are some shapes, typical shapes, hot rolled and cold rolled. They're similar to each other. You can see the locking mechanism here. This is a female portion and this is a male portion. So when you're driving, we can see this is a different kind of locking arrangement here. And basically, each proprietor, when they manufactured these sheet piles, have developed certain, shall we say, proprietary locking mechanisms, the strains, and the, shall we say, moment of inertia. All these actually have allowed them to stiffen the piles and make them capable of taking certain amount of bending moments. Next slide. One more set. Please proceed. Next, yes. Now the sheet piles can be driven. Okay, let's say through most of the soils. And what people found is that when they came to India or place similar to India, where the steel was becoming very expensive, because when you're going to drive the steel actually has to have a high strength for against the driving. It should withstand the stress. And if you use it one time and give it up, then it becomes very expensive. So to control the cost, the multiple usage of the sheet piles were required. So the alloy composition of the sheet piles became very critical, and the cost actually kept on going up. So like people always come up with some replies or to such requirements. So a concrete solution to, or concrete alternative to sheet piles was the diaphragm walls. You can see that you can actually now at the end of the each diaphragm wall, you can see there is a circular pipe inserted here. Now the circular pipe, the sequence is shown properly here. You can actually drill the hole. This tool will show in next slide, and you'll see that the cage is lowered right up to bottom, and you lower a stop and pipe on one end and on both ends. And now this segment will not require a stop and pipe. So then you concrete this portion fully through at least two tremie pipes, because the panels are usually 3 meter to 5 meter in width actually. And just by putting one tremie pipe would not be sufficient. So they put at least two tremie pipes and they are concreted simultaneously. And then when you come to this point, you take out this stop and pipes or the circular pipes, and then the interlock between shall we say, diaphragm walls can be perfectly achieved. Once again, it is endeavored, it is attempted, you try to make this the diaphragm walls also as watertight as possible. May not happen in reality or in practice, but that is an attempt. So sheet piles actually, or the diaphragm walls are basically very expensive, and they are constructed on square meter basis. Okay, so there are some people like B.T. Ganpule in Mumbai who try to devise a method about to use this rectangular piles by piling rigs. So they modified the tools and they try to use a meter wide diaphragm walls. A meter wide diaphragm wall is called meter panel. Of course, there are certain amount of limitations because the use of chisel was not possible in meter panels. So the bite or the penetration of the tools into rock strata was limited. As a result, they found out that the emitter panels were not completely stable. 1 minute. Next slide, please. So for the diaphragm walls, you can see the kind of machines that are used. They're called grabs, and these are tools which are used for to cut even through rock. You can see that these cutters are shaped in this direction, so they go towards the center from both ends and go on cutting a vertical, smooth vertical face right up to bottom. So they're called trenchers basically. Next slide. Okay, this was a site which was done by Epicons, Basel Pharma, and the retaining pipes were designed by us actually, and the actual work which was executed at site, the retaining pipes actually you can directly see how it is done. The one more site you can see. Next slide. Yes, this was a site at Bandra. The diameter here is 1000 and on this side it's 800, and these were also stabilized by putting the anchors. So one more example of retaining piles with the gap in between. You can see there's water seeping through these gaps. Next slide. Okay, so now we can compare the non-embedded wall and embedded wall. Now, we can go point by point function. They're basically non-embedded walls can be load bearing or non-load bearing, because non-embedded walls are actually above ground and the primary function is to divide space or provide enclosure. If you look at the embedded walls, they are basically used as enabling structures to provide support to excavations or slopes. Then in case of designs, the non-embedded walls are designed to resist this significant earth pressure plus probably water pressure, and they also can take help from the internal structural members to prop them up or take the support. Now, in case of embedded walls, they are also designed to resist the lateral pressures, but then by embedding the portion or the bottom portion into the deep into the ground to develop the passive pressure. The support which will come from the for a non-embedded wall is a foundation as well as the internal propping, which comes from structural frame. On the other hand, for embedded walls, it's only passive resistance to soil. Plus, you can actually go look for internal bracing or struts or anchors. The inclined anchors we call tie-back anchors you can call for additional support. Then the applications can be, I mean, in fact, the non-embedded wall applications are very large. The wide range of construction purposes, interior partitions, exterior walls, non-retaining wall applications, or even you can say that supposing you want to segregate in an earthquake zone, suppose there's a hillock slope coming down, and you can put a retaining wall there, and you can segregate your bungalow or your main building from the because from for earthquake considerations also. But then in case of embedded walls, we use them for deep excavations, basement, cut and cover tunnels, and situations where a substantial soil retention is must or required. In case of typical examples would be non-load bearing walls, such as stud walls, load bearing walls such as foundations. Like I showed you all the examples actually, the dams or the compound walls or the various types of walls which are used as already listed above. You can see the various type of constructions are possible in case of non-embedded walls are all used liberally. I mean, you have been designing them quite often. In case of embedded walls, the sheet pile walls, diaphragm walls, or second pile walls are common examples of the retaining walls, which are generally designed by geotechnical engineers. I mean, that's a segregation I would probably like to make. Next slide, please. Okay, now we are going to the concept actually as such. Okay, what is the earth pressure? Now, here I think the purpose of your today's webinar starts. I just gave you some nice pictures and showed you various examples to sort of warm you up, plus warm me up myself up. You can see here there is an element of soil, a small element of soil, though it is shown as a quite big one, but then it's a very small element at depth Z. Now, what is the vertical load acting on that is sigma Z, which is equal to gamma times Z, gamma D or gamma times Z. The pressure acting on the lower side would be gamma z plus delta gamma z, and that's what keeps this element in equilibrium in the vertical direction. Now, what would be the lateral force acting on this? Lateral force acting on this would be earth pressure or lateral pressure coefficient times the vertical load. So that is Ka or K times gamma z. K times gamma z would be the lateral pressure. Now there are three types of lateral pressures. Now they are termed as earth pressure at rest, active earth pressure, and passive earth pressure. Now, what is the meaning of active earth pressure? Let's look at this wall also. Let's say this is a wall, and the wall is not moving. It is standing in its own place. There is no deformation or deflection or displacement. I'm using all the words because one is a translation, one is a rotation. So when this thing is in perfect equilibrium, this is the earth pressure at rest. When the wall moves away from the fill, it becomes active earth pressure, and the wall pushes against the soil, it becomes a passive earth pressure. So let's look at how these things are derived in a brief manner. Next slide, please. Yes, the first concept would be earth pressure at rest. You can see that on the earth pressure, the work was done by Rankine, who was a very renowned physicist at that time, in as early as 1857. So there's nothing new about it. This is as good as India's first freedom fight, actually. He showed that behind the retaining wall, a soil mass actually forms a kind of a failure wedge. Now, let's say this soil mass is going to move en masse or as a body together, rigid body together. It has got a weight W acting downwards. It has got a component which is perpendicular to the plane of failure, which is mg cos alpha, and one component which is parallel to the plane of failure, which is mg sin alpha or sin theta, sin phi, this angle phi, so phi. So when this wall does not move at all, the wall does not deflect, it does not slide. So in response to the lateral of the pressure, the condition is called at rest condition. So there's a zero deformation condition. So K0 is defined as 1 minus sin phi, and the values vary from 0.4 to 0.8. Tarzagi in one of the places says that after saturation or after the wall achieves a steady state condition, the value tends to go towards 0.8. Okay, that is quite close to 1 actually. So that is the first idea. Then let's go to the next slide. Now we are talking about active earth pressure. In case of active earth pressure, the wall actually was there in its own place. There was a wedge. Now you can see the angle of the wedge is different. It was only 5 degree there. Now this is 45 minus 5 by 2. I'm not change the diagram, but the angle is different. 45 minus 5 by 2. And what happens is this pressure actually generates from the wall and it tends to either tilt at top. So I have drawn a diagram with a tilted soil and the soil wedge has moved forward. So there is a deformation definitely at top, which is delta A. That's a active earth pressure coefficient. Now you will see, if you look at, you remember there's a component of the weight which is acting downwards, mg sin alpha, right? Now when the weight starts moving downwards, automatically there will be some friction. The friction would be mu times mg sin alpha, right? No, mg cos alpha, should call mg cos alpha, not sin alpha, mg cos theta, cos phi. Now that will act backwards. Now this becomes a reduction in the pressure actually acting on this. So the active earth pressure is always less than earth pressure at rest. I'm repeating, the active earth pressure is always less than earth pressure at rest. And you will find that the Ka value, the coefficient of active earth pressure, defined by 1 minus sin phi by 1 plus sin phi, is less than 0.5, less than the maximum is probably 0.5. It rarely crosses 0.5. So the reason is that mg cos sin alpha was acting downwards and the component which is acting upwards would be mg cos alpha, mu times mg cos alpha, friction. That friction actually subtracts and you will find that the friction, the load actually is reduced. Therefore, that's why the load on the wall is less. So the value is less. So when you say active earth pressure, that is probably the least possible lateral pressure on the wall. Next slide. Now, on the other hand, you will find that sometimes uh, the wall will be pushed back onto the soil. When you push back the wall, in passive earth pressure case, you push the earth on back on this, and you can see the delta P, the wall is tilted backwards completely. And this wedge has gone up, slid forward, it's pushed up. Now, the wedge shape or the size of the wedge or the angle of the wedge has changed. Now it is 45 plus 5/2. And the Kp becomes 1 plus sine theta by 1 minus sine theta, which is inverse of Ka. And these values are always more than 1. Now that is because, forgive this sine phi, it is cos phi, because the friction component is now, in addition to the mg sine alpha, this gets added up in the same direction. Either in the first case it was subtracting, in this case it is adding up. As a result, the Kp value goes on increasing. Thus, if you'll see, next slide. Sorry. Now here there's a very interesting phenomena which actually happens, we should know. So we have seen at rest, we have seen active earth pressure, we have seen passive earth pressure. So we have deliberately drawn enlarged picture of the deformations here. You can see that this is the earth pressure at rest point, K0. And in case of this wall, the wall is deflected forward, delta A actually has happened. So that value actually has been brought down here. And then as you start, let's say the wall is moving backwards, the amount of deformation that is required for development of the full passive pressure is as much as 10 times delta A, which is very important. So that's why the passive pressure values are very high, and it justifies itself because the deformation required is very high. The interesting point, what we should note here is when delta P dash is equal to delta A, these both are equal at somewhat at midway point, you will find that the PP dash pressure, the passive pressure developed, mobilized passive pressure is equal to half of the full pressure, which means that up to this point, the behavior is practically elastic. And once it starts becoming plastic, it will simply go into failure because you are going for very large deformations, which is a natural phenomenon. So the value of the deformation rapidly increases, but then PP is only 2 times the value here. So passive pressure mobilized at this point is PP by 2, and at this point it is PP. So I think we lost something here, but down. Next slide, please, Jacinta. Thank you. So, though we have seen this, what are the typical formulas we see in C5 type of soil? For active earth pressure, PA, active earth pressure, we use Ka gamma H. We saw the Ka gamma H concept. But then we have to account for cohesion. So minus 2C under root K actually is also added. And the pressure diagram or the pattern of loading is triangular. In case of PP, it is passive earth pressure. Here it is plus, not minus. Kp and Kp both, so the value is very high again, triangular. In case of water pressure, there is nothing, just there is no coefficient because hydrostatic pressure is equal in all sides. There is K is equal to 1, so triangular again. In case of surcharge pressure, which is a additional pressures which you will accounting for, which is a Ka times surcharge. And this is rectangular. And lastly, when you actually insert the returning piles or the embedded type of walls inside the rock, you have to also use resistance to the resistance to failure would be rock shear resistance. So tau bond into B is the what we will get actually, which is also rectangular. Next. So what are the other pressures what we saw? Surcharge pressure. How do they come actually? They come on account of the fact that you will be having a construction materials loaded at site. Maybe labor residing hut pins are there. There will be some in the property adjoining your site. There may be structures existing that may be load bearing. There may be walls. So many other things are possible. Or sometimes or many times what happens now is that let us say we have selected a foundation level as 3 or 4 meters, and then we have to still have to have parking pit inside. Now, if we have parking pit inside, the parking pit may go down to much below our foundation depth. In such cases, you will actually have stepped excavation. So parking pits, tanks, and lastly, the construction machinery which is kept on outside, excavators, cranes, etc., or even the shall we say our concrete RMC trucks. All of them come and actually act as a surcharge loads. Typically, what is done is you take surcharge loading intensity as 20 kilonewton per meter square. But then, supposing you know for sure that the adjoining building actually has loading of 50 ton per meter square, I can use that as a surcharge. Or let us say you are putting a inside the you have a parking pit inside the raft actually, and the raft is loaded to say 700 or 800 kilonewton per meter square, and then the parking pit goes inside. And in such case, much higher known surcharge loading intensity can be used for design of the retaining walls. Lastly, the earthquake effect. As and when retaining walls are part of permanent structure themselves, or if retaining systems are integrated into main structure. Sometimes what happens is, like we did for one of our sites here, I think the foods, Vikran Foods here, what we did, we actually had to use second piles, and those second piles were merged into basement walls. When we did that, the retaining system was integrated into main structure. So the relevant part on the additional forces due to seismic conditions should be also considered as a part of such structures. So this is a point we should not be forgotten. Please take care of that as and when relevant. Next slide. Sorry. So taking a small pause here, we have covered the necessary aspects of how the loads come on that, what type of loads are likely on the retaining walls, and other than that, mostly incidental loads, if there are any, I think they are basically not there. This covers everything. So for non-embedded walls or retaining walls, how do you design? I think this is a very straightforward textbook example. I'm not going to example, but then I'm giving a sequence. We have to ensure that the non-embedded retaining walls are proportioned in such a way that the following checks actually are satisfied, and suitable, I mean, the checks for stability yield suitable results. So what are the checks? First of all, you go for a sigma h is equal to 0. So lateral pressures are equated. See what is the resistance. You always make sure that the sliding resistance or movement translation, lateral sliding portion is factor is more than 1.5. Then the second would be sigma m is equal to 0. Here the factor of safety is always kept more than 2. The minimum required is only 1.5, but you have to keep 2 from the eccentricity conditions. Then third would be sigma v is equal to 0, with the factor of safety is basically 1. Here what we only thing we need to make sure is the Vmax actually, which comes from this equation, that is a total load by width of the foundation, and 1 plus or minus 6 E by B. Now you calculate the eccentricity and put the eccentricity in such a way that the Vmax and V minimum should be greater than 0, and Vmax has to be less than safe bearing capacity. If you achieve these two conditions, the foundation does not go into tension, and so the E is less than B by 6. So all the four conditions, once you actually achieve and proportion the foundation suitably to achieve these four conditions, you will find that non-embedded type retaining walls are perfectly safe. Next slide. Okay, now basically what is the procedure for embedded walls then? The embedded walls are, as we know, we started for embedded walls as the sheet pile walls or diaphragm walls. And we also said initially itself that most of the times these are not used as a part of the main structure. But whenever, as and when they are done, they both sheet pile walls and diaphragm walls are designed to provide a watertight excavation phase, and so the forces acting on the walls are calculated for per meter unit width. There is no gap in between. So you actually use per meter width, destabilizing forces and stabilizing forces on both sides, and you say that the calculation is done. But as and when these walls are, they're supposing that they have to carry vertical load for some reason, then we have to make sure that the vertical capacity of diaphragm wall or steel sheet pile wall is more than the vertical load coming on each column there. Recently, we had one experience we are doing a retaining wall for, or the shore piles or retaining pile design for uh, I think sister helpers of Mary. That's a some NGO actually in Andheri, and the consultant, structural consultant, was forced to take the columns, last row of columns on the top of the retaining piles. So such a thing can happen, and for that the top the runner beam were actually designed separately, and the columns were actually loaded directly onto these piles. Now such a modification is definitely possible. So what you need to make sure is the safe vertical load is greater than the load capacity is more than loads on column, and the factorosity you have already have used load capacity of the piles or the load capacity of the embedded walls. The factor safety is only uses 3 in the calculations. So you have to only make sure that the safe vertical load is greater than loads on the column. So other aspects, see, I'm trying to go back to, if you go back to this thing, we used sigma v is equal to 0. Sigma v is equal to 0, I'm not using here. Now sigma v is, FOS was 1, I'm sorry. So these aspects are same as retaining piles. So we'll present a design of retaining piles in the further sections. Next slide. I think I got a bit mixed up. Okay, design procedure for retaining piles. Now I will start retaining piles as a separate unit practically, because retaining piles have become an integral part of our designs for basement construction now, and they're very important. So we need to understand them very peacefully and step-by-step manner. So there are a number of 3-4 slides will run after this. So please pay more attention to this. Retaining piles are, which is a vertical cantilever beam. It is designed to carry lateral load imposed after excavation. So the lateral load will come only after excavation. It does not carry any vertical load other than self-weight. Remember, for the earlier slide I said that the vertical loads, if required, have to be carried by the safe capacity of pile. In this case, normally we don't have to have vertical load coming on the other than self-weight coming on the retaining piles. So while designing retaining piles, moments and lateral equilibrium is ensured. So sigma h is equal to 0 and sigma m is equal to 0. In addition, deflection of retaining piles, pile head, shall remain within permissible limit from the serviceability considerations. So deflection lateral h is less than the permissible limit. Next slide. Okay, so to achieve the stability of retaining pile, we need to first estimate destabilizing forces acting on the retaining pile. Now, typically these forces are, now here I'm trying to make distinction, because we said that we are actually evaluating forces on per meter width criteria. To go into finer details or make it more correct or make it more accurate, let us say, we actually follow this procedure. Typically, retaining piles are piles of diameter d with an intermediate clear spacing of s, let us say. Therefore, destabilizing forces will act on the width of d plus s. So all the destabilizing forces are considered to act on the width of d plus s. On the other hand, we'll find that, which is the embedded part of the pile or the retaining pile, the stabilizing force will act only on the width of d. So d plus s is destabilizing and d is the stabilizing part. Next slide. So destabilizing forces are, we have gone through this earlier, so I'm just quickly listing them here. Acting on d plus s, active soil pressure, Pa into gamma, this equation is known to you, pore water pressure, gamma W into H, surcharge pressure, Ka into S, and earthquake effect if the retaining piles or walls are part of permanent structure. But normally if it is purely retaining pile, this D factor is 0. Or let us say we are going to construct, because retaining piles are meant to be enabling works and their life is supposed to be not more than 5 to 7 years. So if that is so, then you find that we need not consider earthquake effect. Then what are the stabilizing forces? The stabilizing forces will be acting on the width of diameter d up to embedment depth of d. So I'm going to have calculate the embedment d first. So passive pressure of the soil, once again Kp into gamma h into plus 2c under root Kp, and shear wherever the pile goes into rock or is inserted inside the rock. So P rock is a d times tau safe. That is the bond stress. And if you may use anchors at intermediate levels as and when required. Next slide. So in designing the retaining pile, first you are going to calculate minimum depth of embedment. So first we solve for sigma mi is equal to 0. So we have taken all the forces, destabilizing forces, and this thing, and we calculate the bending moment at the depth d, below the excavation depth. So the bending moment should be taken at the bottom of the embedment depth, which is below excavation depth. It's a unknown initially. We are going to calculate that. So you take the forces, destabilizing forces, calculate moments resultant out of that, and starting as a various lever arm, calculate different lever arms. You calculate the depth, put sigma m is equal to 0, and you will find that you can equate them. But in this case, if the pile is in soil, then you will adopt a minimum factor of safety as d is equal to 2. For the calculation of d is 2. Now, why? Because as and when the pile is embedded in soil, remember this, we saw this, the delta p dash is when the delta p dash is equal to delta A, which is equal, then PP dash is equal to PP by 2. That is a full passive pressure divided by 2. So only half the passive pressure is developed. Since only half the passive pressure is developed, application of this 2 actually becomes effective factor of safety is only 1, not 2. Please note this. Then next slide. Then you increase the length of the, okay, in case of rock stratum, use the embedment depth or use for minimum factor safety shall not be less than 1.5. This is in view of the factor safety already employed, because when you are calculating tau bond, we actually use some factor safety. So that factor safety actually is already employed. So we can actually reduce that from 1.5 to 2. And the embedment depth is then multiplied by 15%. This provides additional factor of safety and also covers likelihood of over excavation below planned excavation depth. Like maybe there is a rock, maybe there is a soil, maybe there is a clay, and you apply the bucket, and my mistake, but if you over excavate, then it should not destabilize itself. So actually increase the embedment depth by 15%. So H plus D into 1.15 times D. That is our embedment depth. Next slide. So then what we do next? Then we put sigma h is equal to 0, put the shear forces to 0, find out which is the point of shear force 0. You can use that, you know very well. I mean, this is a routine thing for you. You will locate the point of maximum bending moment. A typical bending moment diagram would be like this. This is probably just at excavation depth, and this is just below excavation depth, where the bending moment is maximum. Now, when you calculate the maximum bending moment, you can provide necessary reinforcement steel for this maximum value. Next slide. Now it can happen that this bending moment value is much higher than what the section can take. Now in such case, when the reinforcement steel exceeds 2%, the congestion of the reinforcement can happen in the pile section, and therefore in such case provision of the tieback anchor or strut has to be considered or will be considered. Remember, so anchors were required. We had said as a stabilizing measure. Now we reanalyze the retaining pile using the this stabilizing point loads and recalculate the design bending moment. Now the design bending moment has to be brought down in such a way that it is well below 2%. And then you can see that this is the point what we use again, not necessarily everybody does, that the anchor of the magnitude of the anchor is such that you keep you have destabilizing shear force. Let us say that is 100 kilonewtons. Then the capacity of the anchor will try to keep it below 100. That is just to ensure that the negative bending moment is not formed in the pile. If the negative bending moment is formed in the pile, there is a tendency the pile to move away from excavation phase. To avoid that, we actually do this. When the bending moment is positive, the wall will the bending moment, the pile will tend to deflect on the wall. It will not move away from the wall. So negative bending moment is avoided as far as possible. Next. So once again here, that's how you basically design the retaining pile. So embedded type of retaining wall we have designed. Now we go to the next one, what is the permissible deflection for such piles. Now, the retaining piles are treated as a vertical cantilever beam, either propped or unpropped or propped condition. So, but because they are installed by piling rigs, we are calling them retaining piles. Otherwise, they are not retaining piles. They are just simply a suitable construction method or construction technique used for installing the vertical cantilever beams, circular shaped. So they are retaining piles. So once you say word pile, one tends to use codes 2911 or 14593. Now they are not actually applicable for this. For designing, you should use only 456. Next. Okay. So what tends to happen is the permissible deflection criteria is basically a permissible deflection for satisfactory performance is related to serviceability. This is a factor which is known to you again. So in sandy strata, permissible deflection for the in case of active earth pressure is 1 in 1000, and in cohesive soil is 1 in 500. These are both true for active pressure. If remember, deflection is 1 in 1000. If it is going to be passive condition, then it will be 1 in 100, 10 times delta P. Delta P is 10 times delta A. And in case of cohesive soil, it will be 1 in 50 in case of passive pressure. But then normally, for satisfactory performance of structures in mixed soil conditions, you will tend to retain this deflection to 1 in 500, which is acceptable. You might just note that this is also a satisfactory serviceability criteria from settlement point of view. Okay. Now here a point of caution which I would like to raise here, that because of the number of people have constructed number of bridges, you will find that they tend to adopt IRC 78 as a guideline for permissible deflection. And IS code says, IRC 78 says that permissible deflection is 1% of pile diameter. Now 1% of pile diameter is not related to the height of the retained soil. It is not connected at all. It is only related to the section. So in this case, for retaining piles, this condition is not applicable. Next. Okay, now we are going to go back to some questions sent by Epicons, where they talked about what is the submerged weight and where submerged weight is applicable, where you take the hydrostatic pressure or pore water pressure and submerged density, and where you take the saturated density. So I'm trying to first define what is the submerged density and what is the saturated density. So in this competition, total and effective orbital pressure is determined. For the same, you can see that the saturated and submerged density of the soil is required at different depths. You will find that specific gravity of soil and void ratio of the soil are the two main components which require to be determined for calculating saturated density as well as submerged density. If you are determining the E value, that is the void ratio, reliably, you will find that the saturated density value will not be actually at variance or will not be making a large error. So gamma W into G plus C divided by 1 plus C, such an equation if you use. Now, what will happen in case of sand here? You will get values around 1.8 to 1.9. And in submerged density, you see this is whole thing is not -1. It is G -1. So as a result, you will find that this value, if this is 1.8, let's say for 18 kilonewtons, you will find this is about 85 kilonewtons or maybe 90 kilonewtons. No, sorry. 8, sorry, 8. Sorry, mistake. 8.5 kilotons, 8.5 to 9 kilonewtons. If this is 18, this is 8.5 to 9. It is not -1. Remember this. Why is that so? We'll see in next slide. Okay. As you are knowing, already all of us know this, that a soil medium, or let's suppose you take a unit soil mass, it contains some soil particles, it contains some water, and it contains some air voids, which is a gas. So we have solids, liquid, and gas, which is consolidated differently at different places. And the definitions actually for the void ratio are come from this, that VE, that is a volume, this is a saturated sample. The entire void is covered by the water. So this is a saturated area. As and where there is a gas, you will find that that is the unsaturated soil. So when the buoyancy acts on the water, on the soil medium, let us say this is full of water up right up to this point, and the soil mass is then water table rises from outside. Then buoyancy can act only on the solids. It cannot act on the voids, either on the voids or on the water, because it is like saying that I got a buoyancy of water itself. That can't happen. So basically, what we are saying is that's why the difference is not -1, but it is slightly different value. So we need to calculate. Earlier slide, please. Previous slide, previous. Yes, thank you. So that's why this equation becomes important. That is the G minus 1 divided by 1 plus E. So in case of sand, as you said, let us say if this is 18, this will be 8.5 or 9. If this is about 1.9 in case of clay, this will be around about 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 95 to 100 in case of clays. Okay, now we can go forward. Suppose we are trying to calculate the soil pressure. So we have typically taken a case where we have up to H1 height, there is no water table, but then water table exists at depth H1. So the basic soil pressure would be the gamma A1, the first one, gamma A1 into H1 will be here. Then this becomes a constant and goes down. And when you have gamma S, that is a submerged value, into H2 here. Then hydrostatic pressure or the pore water pressure gets added here, and surcharge load as and when there, you'll have to put A1, KA1S and KA2S. Assuming here that the KS2 value is smaller than KS1, we have shown this smaller value. If this can also be like this, it is not necessary that it's different. Okay. So next slide. Right. I can. This is a question asked by one of our friends, I think Sanjay Jadhav. He was saying that under which conditions you can take K0 value. So we are trying to answer to that. Let us say we have excavated for excavation up to foundation depth. Then you put a basement footing or raft, put the basement walls up to first level, put the beam. Once you put the beam, then you can fill the soil. Here, fourth step. Casting of first slab, cast the slab, then you can put this up. In this case, what will happen is once this prop actually has gained the strength, this won't yield. This won't deflate at all. So K0 condition is achieved here. Then you continue this, raise the wall again, put the slab here, prop or the slab in between, and then you can put the soil again. So the K0 condition can be achieved. So this is a pure K0 condition construction. On the other hand, supposing, next slide, if you put retaining piles, next slide, ma'am. Yes, in case of retaining piles, what will happen is, this is a retaining pile. Okay, so what will happen is, at the depth H1, I cannot, unless, because I have to put the prop at this level. So when I come down here, this part will deflate first. Small deflection will happen for the depth H or the excavation depth H1. So whatever deflection happens. This I cannot go back. I put a prop here in place. I cannot push back by putting jack in between. It's not possible. So here, up to this point, K1 condition is applicable. But once you put a prop and excavate below, K0 condition is applicable. So this is a combined condition. So this is a K0 and K1 both acting in this case. Next slide. Yes. That's it. Thanks. नाही झाले सर क्लोज तुमचे फंडामेंटल्स जे आहेत आपण ते पूर्ण केले आता सगळे
We continue or we stop?
We can stop here. If you have questions, I would like to answer questions.
First, let us check whether there are any questions raised in the question answer. I don't think there are. So we'll discuss some few critical points from the point of view of structural engineers. See, all these things, there are 2-3 issues related to this active, passive, and at rest only. Many times what is happening, see, when you are saying active earth pressure, you are talking about the deflection at top.
Yes.
So many times in typically basements, when heights are more and final pressures are there, then there is a obviously restraint at bottom and restraint at some level. But there is a deflection in between also. No? So how that is taken care?
That is a strutted excavation theory where whatever we discussed actually the load distributions or pressure diagrams would be different in this case. They would be more of trapezoid type.
Yeah.
I think Shebeterev actually first name I forgot, but the Russian person Shebeterev actually has come up with those pressure diagrams. They can be used directly.
Then that is okay, but we cannot, in structural engineer's office, we cannot do that theoretical.
No, that is why
we want only whether to use active or whether it's passive or reactive.
You should use K0 condition basically.
K0 condition only.
Yes. K0 condition is advisable because that is on the safer side. And as I said earlier also that even Tarzaki writes down very categorically that after certain amount of time, the K0 condition prevails in case of basements.
So that means almost for all basements as far as structure, except for open retaining walls, everywhere we have to use K0 only, not K.
You would use K0.
Because everywhere basements are tied at top only.
What tends to happen is it is because the K0 coefficient is higher than K.
People are not using.
It becomes, I don't know, it becomes advisable. Sometimes people make some compromise there.
Yeah. Second practical issue is related to cohesive soils. When we are using, rather in structural engineering office, whenever we are using any lateral pressures, we are doing only active pressures and we are not taking the other component of C generally, because it's not because that basic pressure we are considering only active pressures only.
Yes.
That second C part.
Yes.
C part is almost we are not considering, means ignored. So whether it's
I'll answer a question.
Yeah.
See, I think that's something you have to look at very carefully because the parameters defined to you in the report are basically in undrained condition.
Yeah.
Okay. So the failure actually, a slope failure can happen, exposed slope can fail suddenly. But then consider retaining pile or retaining wall. Retaining wall is not going to collapse or fail instantaneously. So that means triaxial UU, triaxial consolidated undrained, and triaxial consolidated drained. These three tests actually are normally done. I mean, we are all aware. We tend to use UU condition. That is an unconsolidated undrained condition. That's a sudden failure condition. So these parameters are slightly on higher side in any case. What happens in sands is that you take C0 and phi is equal to something, say 30, 40, 50, whatever it is. And in case of clays, you take C as a C or CU and phi 0. Now these are extreme values. Actually, in real practice,
both are there, always everywhere.
Correct, sir. So what tends to happen is when you take in between condition, the triaxial undrained, consolidated undrained condition. That means you are allowing the soil to settle down for achieve steady state, and at the time of failure, the failure is sudden. So the condition is separated. So the first is undrained, unconsolidated undrained condition, sudden failure. But we should actually design for the condition consolidated undrained. So when I design the retaining piles, I use the second condition. So the parameters, let us say that I'm going to have a CU value of 10, let's say 100 kilonewton per meter square. I don't use that. I use some factor on that, reduce it down to a lower value, and then add a factor of 5 on that, even in case of clay. Vice versa, for sandy strata, we actually add a small component of C and a lower value of 5. That is a decision what one has to make based on the fines content, then based on the water table condition and loading condition.
But these things are generally not specifically explained in geotechnical report. They are giving only active earth pressures and so that is perfectly okay.
Generic
Science are there.
They are generic reports.
Yeah, they are generic reports. So we have to know that.
But then if you look at our report, I mean, as and when we try to give you a report, we have put those I mean consolidated undrained condition parameters for you.
No, that's okay, but we as a structural engineer, we don't understand that. So I will, what we will expect, you give us some final values for
But
whatever pressure.
in such case, supposing let us say there is a party A and party B, you can ask the question to them, what condition you are given these parameters. If the parameters given are, as I said to you, consolidated undrained, then you should use them directly. If they are not given for that condition, then you ask them for that condition or what
Parameters are not given as a final parameter. Parameters are given as active earth pressure value, and then we are doing 1 minus sin phi, 1 plus sin phi, and applying. So that is
you are given C and phi value, right?
Yeah, that is correct. So C and phi value has to be used for that. That we don't know, now. Okay. Correct. For a common engineer,
there's a confusion when to use saturated condition of that, when to use submerged condition.
I will answer that also.
And before that, so whatever question Pranav has asked first, all the basement is finally constructed. The pressure has to be earth pressure
rest only. Yeah,
It is desirable to use earth pressure at rest, but I don't know whether how much commercial concentration is propane. I have no idea.
2 times. Yeah,
No.
at least 2 times.
No, sir.
No? 0.5 into 1.
0.3 and 0.5. It is not that high, 1.5 times.
Okay. But
No.
okay, this is not being followed probably. आपल्याकडे active
आपण ऍक्टिव्हच वापरतो सगळे.
हे how to make this concept popular difficult आहे कारण पण actual working of the structure, deflection of structure, demand for active pressure rest, not active pressure.
Yes.
Whenever for basement, yes, it is rest. Only for open foundation, open retaining walls, we can use active earth pressure.
True. See, what will tend to happen is, because once you give the guideline very clearly, what actually happens is, because there is no, actually our limitation is like this. A geotechnical engineer ceases to have interaction with the structural engineer after some time, because you are not part of that design team or design group. You tend to actually lose contact, and those additional recommendations or optimization what is required or whatever is actually desired, actually that interaction doesn't take place, because people are in a hurry or in their project schedule becomes very governing, and you start running after that. Once that happens, I think that point is lost out basically.
Everywhere, whether it is a basement in a building which is constructed further, we have to take passive earth pressure. So
Passive, at rest.
Rest and not
At rest condition. At rest.
That is one part. Second is to do दूसरा submerged is
Nice. Submerged saturated.
No, I'm answering that question, but then before that you stopped me. So in case of submerged, what?
Typically asked because it is normally not understood by
Yes.
pressure by a senior engineer.
Yes.
की असं करायला पाहिजे. Active earth pressure can only act when there is a deflection. When you construct the entire building, there is no deflection. So it has to be earth pressure at rest. एक concept popularly माहिती आहे सगळ्यांना असं नाही.
Okay. So when you're designing the retaining piles, I mean, saturated weight, when do you use saturated weight? Now, for the retaining walls and for the retaining piles, the things would be different. Answers would be different. In case of retaining piles, my answer would be that you should use submerged density and water pressure separately. You should add them up separately. And whatever diagram we showed to you, that actually is a very valid diagram. Like upper portion being dry, use gamma bulk there, for not gamma saturated, gamma bulk there, followed by gamma saturated, submerged, and water pressure. If you use that, that is a more correct.
But with the shore pile with spacing, you can
just coming to that point.
Okay.
So in case of shore piles, we basically have, why do you have shore piles? Because we want to carry out the basement construction in monsoon. Correct. So because we want to carry out the construction in monsoon, it is desirable or sensible to use gamma saturated there. and abuse it. We use it. Unless you have second pile. If you use second pile, then once again gamma submerged, and this is because the water is not supposed to pass in.
That's
That turns out to be more, no? Gamma submerged plus.
Gamma submerged,
Plus one is.
no
when
sir.
it turns
You will
into-
see gamma submerged and water pressure will be slightly more than gamma saturated. Maybe 20%.
Third is regarding the pressures below retaining wall. When there is a negative, we can say there is a
Buoyancy.
loss of contact.
But loss of contact.
When there is sometimes there is a such unavoidable situations where then there is a loss of contact for some portion of base.
Retaining wall.
Any retaining wall, any maybe eccentric foundation also, or whatever it is, P by plus M by Z, if there is some tension at some part, obviously, not, but more than B by 6,
Yes.
then that procedure of, and there is a margin in positive pressure. And in that case, whether we can take the soil above and take gross pressures on both sides. You understood, no, what I like. So when you see, normally we are not taking soil above as a stabilizing forces for the weight of the soil above the hill or toe, whatever it is. Okay, as a say normal foundation may not be retaining wall, normal foundation, but subjected to eccentricity.
Yes.
Subject to eccentricity, when there is soil above, we are not taking, and we are taking net SBC.
Correct.
But when there is situation when there is
Understood. You should take.
we should take gross SBC and
Yes.
soil above.
Yes.
That is that if that satisfies no tension, then it's fine.
Correct.
Correct. That is one part. Second part, still there is a small tension. Then there will be redistribution of forces. And the equation changes. So that procedure means we can do it in general as a general knowledge, but that is a very complicated procedure. Sigma V equal to 0 and sigma M equal to 0. We have to match.
Yes.
But whether that is the correct procedure?
It is.
Yeah. Okay.
You have to find out the contact length and.
Contact length and all these things. But then when that because that is a when it is in equilibrium, then any additional factor of safety will be required for that?
No.
It's okay.
No.
I don't think a discussion we should have with our seniors separately.
हा बरोबर ते हे लोकांना माहितच नाही. People are just ignoring ते काय ते शेप मध्ये काय याचे येते ते सगळं सोडून देतात. Pressure. I know, but people are not understanding.
Secondly, they are directly asking questions, what are the softwares you use for finding out the benefit? So basically, all intermediate steps are not understood. And suppose whatever software you are using, suppose we get that software, they can get the answer. Without understanding the entire phenomena, it is difficult.
The nonlinear springs and all such things, tensions are so issue. Loss of contact, that is becomes very complicated.
Very complicated.
Many times. But normal form, as far as if I do it by hand, I will do it like this. PM, J equilibrium will be just satisfied and forget about it. Correct?
Yes, sir.
I just want to confirm.
Very because if you want to capture in the software, why don't you want this?
Stress
concentration is realistic. Take out of the way.
What your questions which are raised by different queries actually all are covered by this presentation at the moment.
When they are asked, they are almost of preliminary.
Yes, sir.
And then we got a feeling that they are not understood, they are not solved any complicated examples. त्याचे पुढचे प्रश्न पडलेलेच नाहीत. ते कुठलं प्रेशर वापरायचं, that was in fact my question. It was not captured.
Yes.
Design engineer, because they have not faced that situation. की काय वापरूया.
Actually, we are not using any softwares at the moment. I mean, because Excel sheet is वापरतो सगळ्या. म्हणजे limit equilibrium method ni we are going ahead. We are not doing the soil structure interaction because that actually complicates the matter very much. आणि त्यात एकदा तुम्ही 3D AFM ला गेलात, इट बिकम्स व्हेरी डिफिकल्ट टू मॅनेज लेटर.
तुमच्यासाठी बोलताना माहित माझं बोलणं संपलं काय करायचं. थँक्यू. येस. राहून गेलं.
Please close.
तुमच्याकडे नाव त्याचं नाव काय? दाते. सत्य.
हा?
तुमच्याकडे जो मुलगा होता दाते ना तो.